to the DeFi Security Summit webinars. We're going to have a webinar every month, and actually we are starting this event with a fantastic line of speakers. Thank you, Nathan, for leading the marketing, actually also in last year in Paris, and also this year. We are starting this month. We have Marius, we have Sien, and we have Ahmad, and I let Fredrik introduce himself and the speakers.
Thank you very much, Muli. Yeah, so I'm Fredrik. I work at the EF in the protocol security team. I have the honor of being the moderator here together with some amazing people. I have a few slides to share what the protocol security team at the EF is doing, but I'm gonna run through them pretty quickly because I don't want to take too much time away from the actual speakers. So let me see. I can fix this. Hope you can see it. So yeah, so the protocol security team at the EF is a group of about 5 to 10 people, depending on how you count it. We have people that work on full-time on protocol security, and we have some people that do it as a side hustle to what they're doing with their primary time. We do a lot of security coordination together with the client teams. Whenever there is a security vulnerability, we will reach out to the client teams, speak with them, try to handle it in a secure way. And we also coordinate with a lot of other people. We do a lot of research on things like client diversity, L2s, threat analysis, and so forth. We also spend quite a bit of time on grants. So we provide grants that are relevant from a security point of view to various actors. It can be universities or it can be just random people on the internet. We also do some incident response in the team and a lot of manual reviews. So we look at the kind of the ecosystem of the Ethereum ecosystem, meaning that we look at all the clients, we look at different libraries being used, we look at the isolated compiler, some smart contracts such as the deposit contract, we look at critical infrastructure, etc. And then we also do some fuzzing, which is a presentation of its own. And one of the key things that we do is that we manage the bug bounty program, which I think is very important. This is the program that people can use to submit bugs. If they find a bug in a client, for example, they can submit it through the bug bounty program, and we will review it. And if it's an actual issue that would have an impact, then we will provide a bounty reward. And as of now, we have the bounty reward doubled up until 2 weeks until the mainnet hard fork of Dencun happens. So at the moment, the max payout is 500,000. Yeah, with that, I'm not gonna steal any more time, and instead I will hand the word over to Marius from the Go Ethereum team.
Hey, thank you. Yeah, my name is Marius. I'm working on the Go Ethereum team, and I'm going to talk a bit about Ethereum Client Security and how to make sure your blockchain doesn't break. So I've been with the EF for almost 4 years now. I joined when we didn't really have a security team yet. The security team was basically Martin, and I tried to help him as much as possible. And since then, the Ethereum the security team grew quite a lot. but since there was basically in the beginning there was only Martin, a lot of the like security related stuff was historically part of the Geth team, and so we've been maintaining a bunch of tools and things there. And I'm just going to go through it a bit. So for those who don't know, Geth is one implementation of the Ethereum protocol. There are multiple implementations in different programming languages. Geth or Go Ethereum is written in Go. Later on, we will also hear from Nethermind, which is the .NET implementation in C#. And Geth is what we call an execution layer client. That means we maintain the accounts and balances. We execute and verify the transactions. We make sure that that once you start up your node, you will synchronize with the other nodes and download all of the old blocks, all of the old transactions, all of the state. And we also provide APIs to interact with the blockchain. So if you want to send a transaction, you will send it to an execution layer client. Or most likely, you will send it to Infura, who will then send it to an execution layer client. And there are a lot of different issues within Geth. The most common types of issues are denial of service, resource exhaustion, and other security related issues. So denial of service, Go is a language that will panic and shut down on runtime exceptions. So if you, for example, access a null pointer, then it will create a panic and shut down the client. And because we don't want other people to be able to shut down the Ethereum network with one transaction or one message, we have to make sure that these denials of services are not happening. And we use unit tests most of the time to help us catch these scenarios. Another big chunk of problems are resource exhaustion. Basically, if someone can create a transaction that will take 10 minutes to run and send this transaction, then every node will take 10 minutes to run this transaction, or every Geth node. And so the network will not progress further. And now with proof of stake, we have a 12-second block time. And so if the block is not executed within 12 seconds, then the next block gets created. But if we have an attacker that can create blocks that are 10 minutes to run, then they can continuously send these transactions and make other people exhaust their resources, and that's really bad for the network. And because we have so much API surface, both in means of like transactions, networking messages, but also the JSON RPC API, attackers can very easily hog resources. So we have to be very careful about the design of the code, and we have a lot of fuzzing in order to make sure that we don't hit these issues where some transaction takes 10 minutes to execute. And another thing is the security of the overall network, of the overall system, because Ethereum nodes are services. They usually run in the background on your system, but they can interact with other things on the system. And so if, for example, you are able to make a Geth node use 3 times the amount of memory that we usually use, then this will have impact on other services that are running on the same system. So unit tests. Unit test is very important for us because it's the easiest way and the quickest way for us to test the functionality. We have unit tests for small functionalities, we have components, and we have subsystems. And the cool thing in Go is that we have great unit test support. It's built into the programming language. And in Geth, we have 12,446 unit tests. which takes less than 2 minutes to run on my machine. So it's a very quick way to cover a lot of ground. And these tests are run on the CI whenever we propose a change to Geth. And so if it's very important to build your components from the ground up with testability in mind. So it doesn't make sense to create a component and then think about testing because it's too late then. Then you have to refactor the whole component again. And yeah, so our components, we try to think about how we can set them up for testing with different, like mocking out different parts of the component from the beginning, and that makes it very easy to test things in your code. Another thing that we use in Go is fuzzing. Fuzzing is basically you call a function that you want to test with random input or interesting input, and try to find errors in it. Either just find panics. So we have 3 different ways of fuzzing. In the first way, we try to find nil pointer exceptions, array out of bounds exceptions, things like this. So trying to fuzz for panics. We have tests where we fuzz the functionality and its inverse. So for example, encoding and decoding, and we make sure that what we decoded matches what we encoded in the beginning. And then we have another mode where we fuzz 2 implementations of the same functionality against each other. This is called differential fuzzing. And so, for example, we have 3 different libraries implementing the signing functionality. So if you sign a transaction in Geth, we have 3 different libraries that allow you to do that. One of them is written in C, and the 2 others are written in Go. And we make sure that all of them do exactly the same thing on the same output. And yeah, so what my whole presentation is about is basically testing needs to be a first-class citizen in your project. And we make sure that whenever we build something, we always think about testing as well. Fredrik already talked about the bug bounty program. That's why I'm going to skip over it. I just want to reiterate that right now, all of the points or all of the payouts are doubled. So if you find a bug and submit it right now, you'll get twice the output, twice the reward that you will get otherwise. And then I'm going to talk a bit about cross-client strategies. So in the first part, we talked about testing strategies for Geth, the client, and now we're going to talk about other clients. And one thing about these cross-client strategies, it's very important to have consensus. So the Ethereum network is run by 5 execution layer clients and 5 consensus layer clients. And so you have at most 25 different combinations of clients. And all of them must work with all of the other implementations, and they have to do exactly the same thing. If one implementation does something different, then we have what we call a chain split. So, for example, when I get a transaction, get a block with a transaction, I have to execute the transaction and make sure that the person that sent a transaction had enough money to pay for the transaction. If now 2 implementations calculate how much the person has to spend to send this transaction differently, then it can occur that one node says, yeah, this transaction is valid, and the other node says, oh no, the person doesn't have enough funds for it. And so they are stuck in 2 different states that don't match each other. One where the transaction was executed, one where the transaction was rejected. And so for Ethereum to work, it's critically important that there are no differences between these implementations. And one thing that we use to find those or to test those is differential testing. Basically, we take the same input and we run it on all of the different EVM implementations, all of the different clients. In this picture, there's only some clients. We do this also on other EVM implementations. So, for example, on the Python EVM implementation or on the JavaScript EVM implementations, and then we collect the output of those implementations and verify that they do exactly the same thing. We have various different ways of doing that, and this makes it very easy to see if something broke, because if two of them, if the output differ, then you know, okay, they decided something differently, and we need to investigate. Another technique that we use is malicious nodes. Basically, we set up a network, a test net or a dev net, and in this network, we introduce malicious nodes. These malicious nodes can insert or alter transactions. They can change fields within the networking messages. They can send big values or nil values. In the consensus layer, we have nodes that can double vote or fake signatures and send weird stuff. So in order to try to break the other nodes. And then we have something that we call shadow forks. Basically, this is something that started around the merge, where we thought about how can we test the merge with. So if we only test our software on the test net, then it's cool, but it's not really tested, because on the test net you don't have as many transactions, you don't have as much state, you don't have as much history, and so what we want to do is basically test everything on mainnet, but we cannot test it on mainnet because then we would people might lose money if we fuck up. So what we started doing is shadow forks. Basically, we configure a subset of nodes with new rules, and then at some point we activate these new rules, and then all of the transactions that are valid on the normal mainnet are also valid on our shadow forks and are being replayed on the shadow forks. And this helped us tremendously around the merge, where we found issues that we would have otherwise not found until mainnet. And this is an overview of some of the testing tools that we use internally, and also with the other teams. So, for example, Go EVM Lab creates state tests for the execution layer. We have malicious CL and EL clients. We have kurtosis and antithesis for running deterministic fuzzing and nightly tests. So we have larger scale test nets being run every night. We have Hive, where we have, I think, 150,000 tests that are being run on every whenever someone proposes an update. Whenever someone proposes an update on any client, they are run on Hive. I think it's nightly or something. And yeah, so we have a lot of different testing tools, and this slide is also kind of old by now, so we built even more. Yeah, and I want to spend the last time that I have to go through some of the stuff that we found, some of the trophies that we collected, mostly during merge testing. So this bug was an issue in the gas calculation in Bisu. It was found by Go EVM Lab, where we created these state tests. State tests are basically just a transaction and some state, and you can execute the transaction and see the result. And here the problem was that there was an issue with the gas calculation, and this gas calculation would overflow. And so what would happen is you would create a call, and then you have basically infinite gas. And this would be really, really bad because you can create blocks that will never stop being executed. And so here, this bug, it's also an older bug, but it also has a bit of a history. There was an issue in return data copy in the Geth code base where the memory returned was shallow copied, and so modifications to the return data modified the memory, and the bug wasn't like, it was kind of bad, but it was quickly fixed and discovered. But we did not announce the bug publicly, and after a few months, someone found the bug and deliberately triggered it on mainnet because they said that only 1% of nodes were affected, but these nodes were inferior nodes by chance, and so it would be really nice if you ever find bugs in one of the clients, even if it's already fixed in the newest version, don't go and trigger it on mainnet. We had a bug in Bisu last week that was also deliberately triggered on mainnet. And yeah, you can go take that bug if you find it. You can go to the bug bounty program and get some money for it, and it's way easier and better for everyone than triggering it on mainnet. Here are some bugs that we found during the merge with the shadow forks. First one was the default gas limit. So in Geth, the default gas limit was set to 8 million. So when we had the first mainnet shadow fork, the gas limit was quickly voted down from 30 million down to 8 million. And if that would have happened on mainnet, it would have been kind of bad because only from the beginning of the merge, the blocks would be smaller, get smaller by 2/3, more than 2/3, and that would have been really, really bad. And another issue that we found during the shadow forks was there were two issues. One of them made us do a 600,000 block reorg, and during the 600,000 block reorg on a girly shadow fork, this exceeded our available memory, and so we were able to rewrite the reorg operation to fix this issue. And another thing was the endianness of the base fee. Basically, the values that we have on the execution layer have to go through the consensus layer, and Prism used the wrong endianness for the base fee, and thus creating a bad block on a shadow fork when the base fee was over 255. Because if you have a value over 255, it uses more than 1 byte, and the endianness only comes into play if you have more than 1 byte. And yeah, so on our test nets, on our small tests that we had, we never went with a base fee over 255 because we just didn't have enough transactions. But on these shadow forks, we did. So that was a good find. This one is a bug that we found with our fuzzers, and basically there was a panic in the math library in the Go language, and so yeah, basically if the modulo was larger than 6,000 bits or 6 kilobytes on kilobits on 64-bit architecture, then the standard library would crash. And this would, like, if you knew about this, you could send a transaction that would crash all of the Geth nodes. And so we had to fix it in the standard library. This was a consensus issue in Nethermind, where the modulo would fail to handle the case of 2 to the power of 255 correctly. This one is a bug, another bug in the modx precompile, and this was found in Bisu, and recently it was also found in Nimbus, where basically you have these 3 parameters. Mod x is x to the power of p, mod x to the power of y, mod p. So you have three parameters, and in the precompile, you have the base, the modulus, the exponent, and then the base, the modulus, and the exponent length. And so if you set the length and the modulus to 0, then the other parameters have to be 0 as well. But some clients did not do the shortcut, and you would result in an overflow. Those were stuff that we found in Nethermind, where there was an issue with the copy opcodes if length was 0 for any of these copy opcodes. And now, if you want to join us, we are still looking for people so we have 2 teams. We have the security team that is very focused on pen testing and fuzzing and active security. And we have the testing team, which is more focused on providing test cases for all the clients, making sure everything works. They maintain Hive, and they maintain the execution spec tests. And for that, we are still looking for people. So if you want to join this effort, you can contact Mario at mario.vega@ethereum.org. And yeah, that was it. Thank you for having me.
Thank you very much, Marius. Very good presentation as always. There are some questions from the audience. I have a question as well, actually, that I want to lead with, and then we can ask some audience questions. So there are a lot of different layers when it comes to security in our ecosystem. So you have end users doing stuff on chain. You have the smart contracts. You have validators and the infrastructure that the validator is running on, and also on the validator/node layer, you have like sublayers such as networking and so forth. So I'm a bit curious of what you feel is the weakest part at this point in time, and what we should kind of focus on improving security-wise.
Yeah, it's a great question. We have a lot of expertise in testing the consensus, like the EVM. Like if there's a bug in the EVM, it's very easy to find for us. So it's not only like finding the bugs or fixing them before they happen, but also if they happen, can we like quickly figure them out? And within the EVM, we have a lot of tools for that, for finding debugging consensus issues. It gets a bit harder if you have issues in the surrounding code. So, for example, if you have an issue in the way the block is constructed, that is more complex to find, at least in the execution layer. I know in the consensus layer they have ways of dumping out the raw block and things, as far as I know. And so that's very cool, and that's something that we should think about as well. And I think the most interesting part for me would be the networking. This is something where we do have some tests. We also have some fuzzers, but we don't have like a very comprehensive test suite for those. We have a test suite for syncing. But this is also not really a focus for client teams, unfortunately. And so people are not looking too much into these areas. And on the consensus layer, I cannot say. I'm mostly focused on the execution layer.
Yeah, it's interesting because if you look at the vulnerabilities that have been discovered, the majority has actually been on the network layer, denial of service attacks, etc. So from a bug hunter point of view, it's probably one of the good areas to look at, I would say. And then we have two questions from Tom. The first one is about when shadow forks are being done. He's wondering if all the different clients are part of the shadow forks, or if it's just like Go Ethereum at one point and Besu at one point. So perhaps you can explain about that.
Yeah, it kind of depends where we are in the cycle. Sometimes we do these shadow forks very early, and then it's only the clients that implement the change up until then. So we had shadow forks where it was only 2 or 3 of the 5 clients on the execution layer. Basically, the shadow forks are only on the execution layer, unfortunately, because for the shadow fork to work, we have to create a new consensus layer with a new beacon state and with a new beacon chain, and so that's kind of how we do the shadow forks. But if we do the shadow forks before a hard fork, then everyone is always on board there. So we try to be as early as possible with these shadow forks because they give us a lot of information, especially, for example, around 4844 now. There was a lot of questions about how's the bandwidth impacted on a node that has like mainnet load with the blobs and everything, the blob transactions in the transaction pool. And so it was very important for us to do a shadow fork quite early in the process with all of the implementations that were ready for that. And but yeah, if we do it like closer to the actual fork date, then there's always everyone there.
Yeah, and then there's the DevNets prior to that and so forth. Yeah. So another question from Tom then is about denial of services on the minority clients. Tom used Besu as an example here. So he's wondering a bit about, let's say a attacker triggers a denial of service on the Besu. He's wondering about the actual impact. Like some people, obviously the ones that has Besu node or client, they would not, well, they would go down, but what would the impact be on the network itself?
So we actually seen this before. There was in the very early days there was a DOS on Geth where Geth nodes it's called the Shanghai attacks, where Geth nodes were not able to follow the chain anymore. And fortunately, we had back in the day parity, and the parity nodes they were able to progress the chain. So Ethereum never went down. Back then, I don't know how the percentage were between the different nodes, but if a client like a minority client has a DOS, it's not that big of a problem as long as the minority client has less than 32% or 33%, because then we are still finalizing the chain. But even if a majority client has a denial of service, it's not the end of the world, because even then the chain will continue on. but yeah, it would be definitely bad. And the client teams that see that there's some DOS happening will have to scramble and fix their software and get out the new release for their to support their clients. And but yeah, usually like the DOS and resource exhaustion attacks are quite obvious why it's happening, and so writing a fix for it is very quick. So like we should be able to write a fix in for an attack like this in like 4 to 8 hours, roughly. So.
Okay, perfect. Thank you. Next up, we have Ahmad from the Nethermind team, who is going to do his presentation.
Hello.
Hello, Ahmad.
Hi. Okay, so I'm gonna share my screen. Right. Okay. So my name is Ahmad Bitar. I'm an Ethereum core dev with the Nethermind team. Today I'm going to talk about Ethereum Client Security and the possible effects of issues in this domain. I'll start right in, no introductions, because it's a hot topic. So in a client, in an Ethereum client, talking especially about whether it's an execution client or a consensus layer client, but mostly I'm talking about execution clients here. There are a lot of moving parts, right? And for each part, there is possibilities of different types of attack on each one of those parts. And we, like the execution client has obviously a database where we keep the storage of blocks, state, etc. It has the EVM and the consensus to process these transactions. There's also the P2P network that we can talk with nodes around it, and also it has a JSON RPC where the users can query this node and ask it about the state of the chain. And there are others, obviously, like transaction pool, for example, that will have transactions up before they are submitted to the blocks, etc., etc. Right. So because we have all of these moving parts and all these parts interact together, there are the attack surface, the attack surface or the security issue surface becomes higher and higher. And we can look at example of security issues that we have seen in clients and other also examples. So for example, there was one that was mentioned by Marius, the Nethermind UNT 256 modulo bug, where when you wanted to do a modulo on that large number, Nethermind wouldn't know how to handle this issue. And this is a consensus bug. There was also a recent bug in Binance Smart Chain where they had two clients, I think. One of them is a fork of Geth and another fork of Aragon, I think. And basically the fork of Geth was their main client mostly. And it had they had a consensus issue between the clients that Aragon wouldn't accept the blocks coming from Geth. And what they had to do was they had to hard code the state transition that happened, the buggy state transition that happened in the Binance implementation of the fork for Geth. And that was like the exact example of a very bad consensus bug issue. that we want to avoid in Ethereum as much as we can. There is other issues in clients. Sometimes in the previously, Nethermind would suffer from a lot of out of memory, and it would be killed by the operating system. Sometimes it would be it would have its memory leak, and that is because of some bug in the code, not handling memory properly. Another issue was one other example of security issues is that a peer would be disconnected continuously because, for example, request or response size is a bit too big and bigger than other clients would be expecting for this request or response, and they would drop the connection from this peer, and as such, this peer would lose a lot of other peers that it was connected to, and it wouldn't be able to progress with syncing the network. You have also examples where database corruptions happen. Data and the database become unreliable. The client would try to, for example, read from the database, but the database won't have the data, or the data would be corrupted, and the client won't be able to progress by processing blocks, etc. There is also the issue that was, I think, also mentioned by Marius, where the Go Ethereum implementation transaction pool on Gurley maxed the CPU usage, and this is a very simple example of a DOS denial of service attack. Ledger, even though Ledger is not an Ethereum client, but the way the hack happened was very interesting, where the hacker utilized access on a GitHub repository, on a GitHub account, to run a GitHub action that would publish malicious and vulnerable implementation of the Ledger Connect, whatever library, the library that, and because Ledger at the time used to allow clients to pull this implementation from a CDN, then these users in the browser were pulling the vulnerable JavaScript library every time, because the hacker was able to publish this vulnerable implementation. So this also shows how bad it could be if, for example, someone with authority to publish a client, for example, can publish a client that is buggy. That's why we tighten the security around our GitHub repositories as much as we can. Now, let's explore more on these components that were mentioned before. What possible issues? And these are just examples. Again, they're not everything, right? And we will look into each. How big of an issue each one is, right? How big of an issue in each situation. For a minority client, for a majority client, etc. We're going to look at it. So, for example, the P2P network, if you are able to do a DOS or a denial of service, for a minority client, it's not that big a deal. For example, Nethermind can drop. The network can still finalize. It's not higher than 33%, for example. It's the network can still finalize. Everything is fine. It would be bad for those ones running Nethermind, for example, or any other client that is a minority client. But it won't affect the network as a whole. The network would still be able to finalize and progress normally. Synchronization issue, for example. So if, for example, a client is not able to, new clients not able to sync from scratch, then this is not that big of a deal, because only new clients are affected, or new nodes are affected, but existing nodes are progressing normally. So this won't have that big of an effect. Same with database corruption and consensus issue. If a minority client has it, that's not a big deal. It will just fork on its own, and the network would still be able to finalize. this client would probably fix the issue later, and it would join the correct fork and would start attesting to the correct fork again. Not big of an issue. Same thing for consensus issue, AVM with AVM and consensus, not that big of a deal. If we look at JSON RPC transaction pool, we already talked about denial of service for a minority client and what would happen. It would just be denied till the issue is fixed. Like Marius said, probably 4 to 8 hours for denial of service. If it exceeds, I would be surprised if it exceeds 1 day to be fixed and released to the public. Now, looking at these issues from a perspective of a majority client is a completely different story. When we look at a majority client having a denial of service attack, then we would suddenly have finality dropped, and that's one of the cases, right? Finality dropped, and when finality drops, something happened called an activity leak in Ethereum. And when an inactivity leak starts happening, all of these not being able to attest because they got DOSed, right? And they were running the majority client would lose, start losing part of their stake that would increase quadratically with every epoch till they lose, possibly, could be, all of their stake. So it's really scary. Synchronization issue is the same, like only new nodes can sync, so it's not that big of a deal. Now, let's talk about database corruption. So if database corruption leads to a consensus issue and not just an inactivity leak, then that's a totally different story for a majority client, because here we're talking about more issues depending on the percentage of that majority client for the validators. We will discuss this more in the next slide. Same with consensus issue, it's very high, critical. Denial of service, as discussed before, for a majority client would lead to an activity leak, and the more time that these clients are offline, the higher the penalty for being offline and not attesting to the network. So this table here specifies what would happen depending on the client's validator market share, right? So if the client is below 33%, if it went offline or it had a consensus issue, then there's no significant impact. The chain will still be able to finalize. There will be no big penalties, because all the penalties that these clients would endure is just the normal missing attestation penalty, which is not that high, and it does not increase quadratically. Where if the client percentage is between 33 and 60%, 66%, then the chain will stop finalizing. And if it's above 50%, so there is 3 thresholds, right? There is the 33, there is the 50, there is the 60%. If it's above 50%, then we would end up with 2 chains, and that would start being problematic, right? But neither chain could finalize. So if things depend on finalization, like bridges, for example, or deposits in decentralized exchanges, etc., then we are still safe, kind of, right? If they're built right. And the inactivity leak kicks in, resulting in penalties that increase quadratically every epoch. And that's really tough, because we will see in the next slide what happens with these increases and how bad they are. And also, for the rest of the stakers, they stop receiving attestation rewards, but they don't endure any penalties. And there is a reason for that. The reason is that if they keep receiving attestation reward, then they have an incentive to keep the rest of the network offline, because they would get more. So it had to. We had to also prevent them that already attesting nodes from trying to do that, right? So what would happen if we are talking about more than 66% of the market share of validators? Then we have very problematic outcomes, right? So what would happen is that the majority client would be able to finalize an incorrect chain. And if exchanges and like, for example, stable coins that have backing, etc., there will be a lot of consequences because they can depend on transactions that land in this incorrect fork to deposit money for people, to allow people to withdraw money, etc., and we would end up with two forks, one that is finalizing but it's incorrect, and the second that is correct but cannot finalize, and it's in an inactivity leak. And what happens is that, so we have two choices. We either accept the bug and we make all the other clients buggy, just like the majority client is buggy, and then we forsake the good forks that don't have the bug, right? Or we have another solution, which is to forsake the buggy chain, but then it was finalized, and probably some people already did certain or a lot of transactions that possibly gave people money and etc., and they can't go back on these transactions after we decide, okay, we're gonna forsake this finalized chain, right? This finalized fork. So it's a very big deal. So there is, okay, now looking at inactivity leak, what would happen when there is a majority client that goes offline, meaning anything above 33% would lead to an inactivity leak. And here we look at, this is a chart from Dankred article called "Run the Majority Client at Your Own Peril," right? And here this graph is actually very, very old. It's from 2022, March to 22. So the actual graph of what's currently on the beacon chain, the value of the slope is way higher. So what you're seeing, that the blue one is for sure not the one that is running right now, and not even the red one. It's even slopier and higher. So it goes way faster with the inactivity leak, to the point that in Billatrix the value was set that the inactive validators would lose 60.7% of their stake if in only 18.2 days, which is 4,096 epochs, right? And that is, and the reason that the inactivity leak happens is to if a majority of the chain started going offline, the chain can start finalizing again once these offline validators their stake goes low, and the rest of the validators can then attest, and they become the majority again. So they become more than 66%, and they can finalize the chain. So as you can see, that even this red, very scary line is actually not representative of what the value is set right now. It's really scary for all the validators out there running a majority client. And like, I would highly advise any validator, especially institutions running a majority client, to switch as soon as possible, because in their risk assessment, they need to keep that in mind, keep this risk, huge risk, in mind, right? So right now, the state of client diversity, you can look at the website called clientdiversity.org, and unfortunately, this is very unreliable data. For consensus client, the data, there is multiple ways of calculating the data. So one of them actually crawls the P2P network to know how many CL nodes are out there and what is the reported client that they're running. But this is not representative of the validator node. It's representative of just the CL nodes, the number of CL nodes that are running. Another way of calculating these numbers is using the format of the block to use an algorithm where they would know if it's formatted more like the produced block, if it's formatted more like Prism, Lighthouse, Tico, Nimbus, Lodster, etc. And obviously, this mechanism, it's not that accurate, right? Because there could be a lot. There is obviously a lot of similarities between the produced blocks and CL clients, and the accuracy of this method is very low. The last one of the ones that are presenting the data, we do not even know how it's collecting the data. Rated network, it's closed source. For the execution client's data, there's a website called Execution Diversity, and what they did is that they went to institutional stakers and they started asking them, what type of execution nodes are you running? And this is the reported data that they got, and they only covered like 60% of the network, and that's not even that much updated. So the institutions could be changing this data without informing execution diversity.info that they have changed execution client. So this data is super unreliable. I will give some alpha that this is about to change, hopefully soon, and we will hopefully have reliable data, but I can't say anymore. So what I was saying is that client diversity is a bit complex, because if you go and look at nodes in the network and you ask them what client are they will report it, but that doesn't mean that's representative of the validator diversity, because validators, you can run thousands of validators on the same node without issue. So that means that just knowing what the nodes are running does not mean that it's the same representation for validators. Same thing for builders, especially with MEV. We have builders always building the blocks most of the time. We're talking more than 90% of the time builders are building the block nowadays. And that results in, if all the builders are using the same exact client, then we would possibly, and this client introduces a bug, there could be a possibility that we will have always no blocks, because every block would not be able to be included in the network because the other clients would reject it, right? And this is problematic, obviously. And that's a wrap. I would like to reference Dankrand's article and the ETH2 book, ETHtaker's article about client diversity also. Clientdiversity.org for the statistics, and thanks to my colleague Marek for his help and review on the presentation. And yeah, that's all from me.
Thank you very much, Ahmad. I think that was great. I think the way you made the security issues surface very visible was very clear. I think that was really easy to digest. And I think one of the key things is probably that you showed the risks of actually running a majority client, that it can impact you in a very negative way if you do that. So there are, of course, risks of running a majority client, and people should definitely consider running a minority client. Yeah, on the diversity part, I think, yeah, that's really interesting, and I think you can probably expand it even more, like thinking about, you maybe don't want to put your validators on AWS, for example, because a lot of other people might do the same thing, and if AWS were to go down, for example, that could also impact your
100%.
So home staking is definitely something that's worth considering. We had a question from Xiao Quan. I hope I pronounced the name correctly. Xiao Quan was wondering about a bit about client diversity. So basically wondering, what is the major reason that people are staying with Geth as the majority client and not switching to Nethermind, for example? What do you think about that?
Right. So first, Geth is a very good client, right? And it's one of the best, actually, if not the best. And that the Geth team are one of the best client teams that can work on a client. So it performs really well. It has very high performance levels for validators, and like when you look at institutions, which are unfortunately mostly who run the validators, especially with Lido dominance being around 33% of the network, you would see that these validators are always optimizing for the highest effectiveness. And if even Geth is better by 1% than another client in the performance perspective, for example, then these institutional validators would choose Geth because this 1% to them is a lot of money left on the table, and they wouldn't want to leave it on the table. Of course, this is only one aspect. Right now, Nethermind has been seriously improved in the performance perspective. Previously, Nethermind, for example, used to require more than 12 gigabytes of RAM, for example, to run. Now it requires less than 4. Previously, Nethermind had, for example, a lot of missed attestations. Now, almost never missed attestations, right? There was a lot of optimizations done on Nethermind. So till people are used to seeing these minority clients in the lead when it comes to performance, it will take some time till they adjust to this change. But yeah, that's about it.
Yeah, and I guess today a lot of blocks are being built by external builders as well. And I think a lot of those, or if not all of them, are using Geth, which could be a bit of an issue as well, I guess. That needs some work. You mentioned the Ledger Connect hack, which was a very interesting supply chain attack, in my opinion. Nethermind, like basically all software today, use various libraries. So you mentioned that you secured your, I'm guessing your team's accounts, for example, making sure that they're secure and so forth. But how does Nethermind protect against supply chain attacks? On the libraries you're depending on and so forth.
Right. So we basically don't just take the latest library and start running it on Nethermind whenever it's available, right? And Nethermind does not have this automatic way of pulling these libraries. Nethermind needs to be built with a specific library number. That's how .NET and C# work. You have to specify the packages with versions, specific versions. So we tend to test run all of our updates when it comes to these packages. When we update these packages, we test run the client, make sure it's running smoothly. We run the fuzzers and we make sure that no issues are happening because of this NuGet update, whether it's a regression in performance or anything else more serious.
Okay, perfect. Thank you very much, Ahmad. The next speaker that we have now is Sean from Sigma Prime.
Hey, how's it going, everyone? Let me just share my screen here. Okay. So I'm Sean. I work at Sigma Prime. I've been working on the Lighthouse client for the past, I think, 3 years now, maybe 3.5. And I'm going to talk about security on the consensus side of things. So a lot of the concepts will be similar to what we've been talking about with the execution layer, but there's a bit of a different context that we think about them in. And there are some unique sort of problems that arise from dealing with things like fork choice in the consensus layer. And we've been able to develop some interesting tools to deal with these types of problems, to try to like find bugs and issues in implementation more quickly. Okay, so first I'm going to start with just understanding the sort of core issue that the consensus layer specifically is trying to solve. And that's related to like deciding which chain is the correct chain. So coming to consensus on what is the correct chain. So if we start with a single block and this block's valid, and then another block is built on top of it, pretty easy to come to consensus like block 2. This is now the head of the chain. However, if we have a third block that enters the picture, and this block is also valid, but shares the same parent as block 2, now it gets a bit more confusing. Do we pick the latest block, or do we pick the block that we saw first? Because with these two blocks sharing a common parent, they're going to lead to different chains. Okay. So in proof of stake, we have this voting mechanism to determine these sort of tiebreakers. And this is the collective weight of the stake behind attestations that validators are making. And I'm not going to go too deeply into the details of it, but this sort of weighting mechanism is how we resolve these types of issues. And other ways in which determining the correct chain can fail, we've talked about them previously, but it's related to chain splitting. And this would have to do with message validity. So when I say message validity, what I'm talking about is, do different clients or different nodes, when they see a message, do they have the same rules implemented about like, is this valid or not? Because if one determines it's invalid, for example, block 2, they might discard it and never look at it. Another node might have identified it as valid, imported it, and started building on top of it. The node considering this invalid would never be able to like, come back and import that block and reorg to the correct chain. So this would be a chain split. We mentioned it in the execution layer with regards to like making sure the EVM functions the same across clients. But in the consensus layer, we have similar, like we need EVM correctness, but we also need, and we rely on the execution layer for that. But we also need to make sure that the management of the validator set and the interpretation of attestations that validators make are consistent. And so that's related to like the message processing, the state processing that we do. Making sure that these are on the same page will limit chain splits that are persistent. But there's also a component of message propagation, so making sure everyone sees the message. If you aren't seeing votes on block 2 in this scenario, then you would think that the weighting on block 3 is higher than the rest of the network thinks. So this may cause you to remain on the minority fork for longer. And there's also this timing component to fork choice and picking the canonical chain. And this timing component's introduced by the fact that validators are required to vote at a specific time in the slot. And so that's at 4 seconds. So what you're really getting is like an aggregate view of nodes with different stakes, like what is their view of the chain at this time in the slot. And from that is where you make decisions about which chain do I go along with. And failures in any of these previous errors can lead to things like reorgs. In this scenario, what would happen is anyone who had set block 2 as head and voted on block 2, if later block 3 ends up getting more weight, they would have to reorg to block 3. So sort of discard block 2 for now, change to block 3, set that as their head. And in this scenario, typically, like whoever is building block 4 would have a lot of weight in determining which of these 2 chains ends up being canonical. There's a lot of details related to that. And then there's also the impact of offline nodes on consensus. And we talked about this in Ahmad's talk, where once you hit certain thresholds, at that point you can no longer finalize the chain. And so, for example, if 1/3 of the nodes are offline, then finality won't happen. You start getting the inactivity leak. And the other very important component of this, from the perspective of the consensus layer, is that the longer you have these periods of non-finality, the more possible blocks you have to keep around in order to like potentially make a reorg, and also the states corresponding with these blocks you have to keep around. So this is the same sort of structure, but introducing what are the beacon states. So these are the states associated with the consensus layer. These are the current state of the validator set and the state of the chain based on how the consensus layers applied all the blocks leading up to this state. So each one of these states on the left is sort of like an intermediate between different blocks. And in periods of non-finality, we need to keep more of these states around in order to potentially apply these blocks to find different states, because there's more possible chains that we have to consider when deciding what is the head of the chain. And these states end up being like a big deal for us because they're a lot bigger than blocks. So blocks are somewhere around like I think 100 kilobytes, whereas the beacon state right now is somewhere around 100 megabytes, over 100 megabytes. How this changes in Deneb is we're adding blobs, which are more similar to blocks in terms of size. They're also around 100 kilobytes each, and we're adding 6 of them, but they don't actually increase the size of the beacon state. Yeah, so managing these states becomes like a big problem from my point of view in terms of like thinking about how we want to design parts of the client, because the easiest way to take down a client might be making it use a lot of resources in either holding a lot of states in memory or making it dump a lot of these states to disk. And this would typically happen in periods of non-finality. Once we have finality, we have like some set of assurances that we won't actually need these states again. So what we do is we end up pruning them pretty aggressively. So we by default store 1 state every 2048 slots once the chain is finalized. And this is because like we have assurances that we won't reorg to that chain unless there's like a mass slashing event. Okay. So yeah, in terms of security, I think about like, how would I do the most amount of damage possible to the Ethereum network? And we've touched on this a few times, but a chain split, I think, is maybe the most damage you can cause. And the specifics the specific version of a chain split that is the worst is when something that's invalid is finalized. And this is because when you have something invalid that's finalized, you can't vote on a different chain without being slashed. So as Ahmad mentioned in his presentation, it's either you keep going with the invalid but finalized chain, or all these people are going to lose their stake, a large portion of their stake. Yeah, and then the other component here is you can do a lot of damage to the network just by inducing an outage. So this would be like a DOS, like we've been talking about. I think of this oftentimes more in terms of resource usage generally. And that's because you can cause clients to miss their caches frequently if you have things like a lot of forks or maybe like unexpected scenarios related to forks that could cause clients to do like a lot more processing, or maybe look at their database more times than they expect. And then at some point you can get to where the machine they're running on can't actually keep up with catching up on this old processing, as well as like doing new processing related to staying with the head of the chain. So there's a scenario where you're slowing chains down enough to where they can't keep up. And also there's obviously the risk of just fully exhausting resources on the machine that they're running on. And so this isn't necessarily as bad as finalizing something that's incorrect, but it still is bad in terms of if enough of the network's offline, all of a sudden the chain isn't finalizing, and then that sort of like compounds things because all the nodes have to keep more blocks and states around and handle the potential for longer reorgs, and this increases like the RAM and disk all nodes are using. So there's sort of like this compounding effect there. Yeah, so generally we have a strong focus on like correctness in order to avoid a chain split. And Marius talked about this with validity a lot, where like you can do things like differential fuzzing to determine our clients like acting the same in a lot of different ways. I found that with the consensus layer, we have like a common set of tests related to message processing and state processing that all clients run against. And this has been really good to alleviate the potential for, if a single client is writing their own test for all these scenarios, well, one, there's the risk of maybe you wrote the test incorrectly, but then there's also the risk that you're testing your implementation more than you're testing the actual functionality. So having this common set of tests that all clients run against helps with us understanding functional differences, and it also, to some degree, reduces the amount of like duplicative test writing that we end up doing. Yeah, and so another thing related to this is multi-client testing generally. So whether that be on like local test nets or just network simulator type tools, testing across client types, but also client versions, because it's possible that across different versions of your client, you change something in consensus that causes it to be incompatible with either a prior version of your own client or someone else's client. So there's this interoperability component that gets like pretty complicated and tough to test pretty quickly. Yeah, and I wrote this point, fuzzing. Generally, this is good to find stuff related to like invalid data in your specific implementation. How does your implementation differ from others? And I mean that in terms of like a more granular level related to specific messages. Whereas we can also get into fuzzing in like a different way, where you're fuzzing related to maybe messages that are valid but coming at different times, or valid but also intentionally able to like induce forks in certain scenarios, things like that. And that's where this like timing propagation type chain split comes in. And this can be related to like a fork choice implementation, which I've done some work on in Lighthouse in the past, and the fork choice rules, they get pretty tough to follow because there's this degree of like self-referential nature to them, where you have like an attestation that votes simultaneously on the head of the chain and the part of the chain that's finalized. The head of the chain can never diverge from like the finalized part of the chain, so it can't like switch from that part of the chain. But also the weight at the head influences what becomes finalized eventually. So there's a lot of scenarios with this, especially related to like if different views of the chain, like different nodes are seeing different messages, then they might have different like fork choice states, and these states might need to be resolved if, for example, like there's a temporary network partition. So tools for network level simulation are really helpful for this. Kurtosis is useful for this. So is antithesis. I think with antithesis, you can even manipulate like the timing of each node and also like the latency of messages across the network, which is cool. And then this tool, Blobber, is one made by Mario at the EF, which I thought was really cool. We had found an issue in Lighthouse where on one of our Deneb testnets, we were trying to import a block from a peer using the same rules that we use during gossip propagation. And what happened was our gossip rules prevent you from importing like the second message you see. So if you got the second message, then the first message was the one that was actually voted to be valid. You'd have to go get it from someone else. But if we weren't able to import this block, this blob, then all of a sudden we can't import the block generally. So then our chain or Lighthouse nodes, we get stuck, wouldn't be able to like proceed with the correct chain. So I brought this up on a call, and Mario, he went out and built a tool to test not only this specific scenario, but also other types of scenarios related to blob message ordering and timing and validity. So that was really cool. And this next bullet point is Hydra fuzzing. So Hydra is this tool that Michael from our team has created, and I sort of alluded to this before, but what it does is it tries to target fork choice specifically. So it creates valid blocks and it creates valid attestations, and it's aware of the types of thresholds related to finalization in order to like get you near those thresholds and also induce randomness around those thresholds. And this can help with understanding if Lighthouse might behave differently in more extreme situations to other clients, or if we have a fork choice bug that we can't recover from. But yeah. Okay. And so this other aspect of client development is staying online. So I think in terms of like resource usage, a lot of times when I think about resilience, there are others on our team that are more focused on, for example, like making sure like a random packet can't crash Lighthouse. But for me, I work a lot more in this fork choice area where like we're dealing with more states. We're dealing with what happens when we have unexpected reorgs with like maybe 5 different chains when we only want to store like at most 4 states in memory. Typically we try to just have one state, and in like normal processing, we're just mutating the state and keeping it in memory. But every fork essentially adds one state for us, but there has to be some threshold at which like we don't want to use even more RAM. And at that threshold, we'll either have to like just dump a state and later, if we end up needing the block related to it, load the most recent state on that chain from the database and reapply blocks. So in that scenario, you're trading off RAM in order to do more processing. So you're using less RAM, but doing more processing and loading more from the disk. Reading a state for the disk, for example, is something like, I think 250 milliseconds up to like 500 milliseconds, maybe longer. And then processing a block is somewhere around 100 milliseconds. So you have to think in terms of like, okay, if we save 100 megs of RAM, like what are the odds we might actually have to do this much more processing later? That goes into a lot of like the caching decisions. And then there's also these same sort of issues with like timing and message propagation related to just staying online generally. And this is because like a lot of these scenarios where we have like either network partitions or we have messages being withheld and released later, these are what can induce the sort of worst case resource usage in our clients. So the same sort of tools are also good for understanding worst case resource usage, and that's something we like end up focusing on a lot of the time. And then this last point, tree states, is actually an upcoming set of changes that Michael from our team has been working on for a while. And to illustrate it, I'll bring back this slide. And so here you can see that every time we mutate a state, we're essentially treating it as a new state. If we do a reorg here from block 2 to block 3, we have to dump state 2, and we have to reload state 1 to find out what state 3 was. But in tree states, we would treat state 0 as like, this is the base state, and then every time we apply a block, we just track the diffs. So this would allow us to use a lot less RAM. Instead of using like 100 megs per state, we would end up using, I think 100, we'd be able to store 128 states in that same amount of RAM. This would make us like a lot more resilient to reorgs. It allows us to do a lot more caching. We wouldn't have to worry as much about cache misses. And then on top of that, we can have the same sort of storage structure in our database. So the states that we are storing and the ones that we have to keep around when there's long periods of non-finality, those also get smaller. Yeah, this is an exciting set of changes Michael's been working on for a while. Our tentative plan is to release this after the Neb hard fork at some point. Yeah, so that's about it for me. Thank you.
Thank you very much, Sean. Yeah, so it's a very complex and very niche topic. So yeah, very impressive that you can make it so easy to understand and yeah, digestible. Given that it's a very niche and niche topic, do you have any suggestions on where people could start to read more or like research on it if they're interested in it?
So I really like the annotated specs. There's a set of annotated specs that Vitalik wrote, and then also Ben Edgington has, I think it's called the ETH2 book. I found those both really useful. And then other than that, for me personally, I didn't really get a deep understanding about a lot of this stuff until I tried to actually make some of the changes. That's sort of how I fell into client development, I think, is that I hit a wall with how much yeah, I hit a wall with how much I thought I could learn by looking at the specs, and then trying to make a change, you end up learning a lot more. Yeah.
Okay, there's been a few questions. Mooley asked, what kind of problems does hydrofuzzing detect?
Yeah, so we can actually use it for a lot of different things. I'd say the general idea of it is trying to cause as much chaos as possible with valid messages, like messages that Lighthouse or any node has to process, any consensus node. And so these would be like attestations or blocks, specifically where we're looking at the consensus information in a block, not so much the payloads. And the idea here would be to induce reorgs as much as possible. And this would be testing our fork choice implementation. So deciding like which block everyone should vote on for the head to try to like restore stability. But then on top of that, it's also really good for us to understand what our resource usage looks like in the worst case, because a lot of our caching is based on like, this is how we expect the chain to run most of the time, with some margin of like, this is how much RAM we'll dedicate to ensuring that in a bad case, we can still run fast. But then there's some limit to that where like we just can't store everything in memory. And so understanding those scenarios better is also really helpful from Hydra.
Cool. So Tom had a question. I'm not entirely sure if this was targeted towards Ahmad or you. I didn't see it, but I'm sure you can answer this in any case. So in the case of a denial of service, if you want to have as much impact on the network itself, would someone be attacking the execution clients or the consensus clients?
It's a good question. I think maximal impact, you probably would want to target Geth, just in terms of like the usage. I think you could end up doing I would say equal amount of damage, because on either side you can cause both a consensus split. So if you can figure out that something in the consensus layer is different, that would cause either like their notion of what is valid to be different, then you can cause a consensus split. And also resource usage. For us, like we don't have anything built in like the EVM, so I personally don't understand, or I don't know what the impacts of like understanding the DOSability of the EVM are, for example. I'm more just focused on resource usage generally, but I think the execution layer also has those types of problems.
Yeah, yeah, sure. Marius has a question. So he's asking about how EL clients store diffs between states. And he thinks that that's not possible on the consensus layer because of the state being able to change completely between blocks. So on the consensus layer, do you think it would be possible to bound the changes between blocks?
So let me think. I'm not sure about the ability to bound the changes, but what I would say is like the risk of the state changing completely is lower on the consensus layer because the state is only 100 megabytes, and we are already holding multiple states in memory anyways. I'd have to think pretty hard about the scenario that would actually cause the entire state to change at once, but yeah.
Okay, one final question then. Do you have any favorite Lighthouse vulnerability that showed up throughout the years?
Okay, let me think. Favorite Lighthouse vulnerability. So I feel like I'm more proud of having found a vulnerability in the consensus specs, and that was related to fork choice. And that was related to a specific scenario with proposer boost, where you're adding an extra artificial weighting to whoever the block proposer is when trying to figure out what the head is. So I was proud of that, one in terms of like it's pretty hard to find spec bugs because people think really deeply about the spec, and then two, just because fork choice itself is really difficult to reason about. So I spent like, I don't know, 8 hours just thinking through like specific scenarios, because Lighthouse was like not acting how it should when I was trying to run against the EF tests. But yeah.
Okay, thank you very much, Sean. I will hand over the word to Muli then.
Yeah, so thank you very much, Marius, Ahmed, Sean, for the fantastic presentation. I really learned here. Thank you, Fredrik, for moderating in such a nice way. And thank you, Nathan. We will actually post, hopefully tomorrow, the recording. And thank you, everybody, for attending, and looking forward to seeing you in the next presentation. Thank you, everybody, for attending. And thanks again, Nathan, for organizing, and David. Thank you, everybody. Bye. Happy New Year.